In this section, we'll take a look at applications of the law of sines. And here's an example. To determine how far a boat is from shore, two radar stations, radar station A and radar station B, that are 500 feet apart. Let me go ahead and just mark that on here. They're 500 feet apart. Find that the angles out to the boat are 70 degrees and 60 degrees as represented in the figure below. Part A. Without any computations, how can you tell that radar station A is a shorter distance to the boat than radar station B? Okay, so let's take a look here. Radar station A and radar station B. So let's label the sides across from those radar stations. Capital A is representing radar station A at 70 degrees. So the side that is across from that, let's call that lowercase a. And the side that's across from radar station B at 60 degrees, let's call that side B. And what I know just from looking at this picture is that angle A, capital A, that angle of 70 degrees is larger than the angle at B, which is 60 degrees. So if that's the case, then the side, lowercase a, must also be greater than lowercase b. So let's see here. Here's the question. Without any computations, how can you tell that radar station A is a shorter distance to the boat than radar station B? So the distance between radar station A and the boat is that length of B, isn't it? And we just said that B is going to be less than A. So that is how we tell. So maybe we write something like this. Since angle A is greater than B, then side A is greater than side B, and side B is the distance from radar station A to the boat, and therefore it's a shorter distance. All right, so that's part A. Part B, let's talk about part B. Determine the distance of the boat from station A. Round your answer to the nearest whole foot. All right, so we want to actually solve for this length of B, and B is across from that 60-degree angle. So I can use the law of sines, and I'm going to say that side B over the angle across from it, 60 degrees, is equal to, now do I have an anchor? I know the 70-degree angle, but I don't know A across from it. I know 500, and I was not given the angle across from it, but I think I can find it, can't I? Let me erase some of this because it's so messy. Okay, so if I know 70 degrees and I know 60 degrees, then that tells me that this angle right here must be 180 degrees minus the 70 degrees minus the 60 degrees, which is what? 50 degrees? Does that sound right? 6, 12, 130, 50 degrees? Okay, so that's a 50-degree angle. So I'm going to set this B over the sine of 60 degrees. I'm going to set that equal to 500 over the sine of 50 degrees. So what was given to me in this one was the angle, then a side, and then an angle. Angle, side, angle. And we know angle, side, angle, we can use the law of sines. We just had to do one extra step to find that third angle. Okay, so I'm going to multiply both sides of this equation by the sine of 60 degrees, and that's going to get me that B is equal to 500 times the sine of 60 degrees all over the sine of 50 degrees. I'm going to put that whole thing into my calculator, And when I did that, I got approximately, rounded to the nearest whole foot, it said, I got approximately 565 feet. So the question was determine the distance of the boat. So I'm going to say the distance from the boat to radar station A. Radar station A is approximately 565 feet. Let's look at another example. In order to estimate the height of a building, two students stand at a certain distance from the building at street level. From this point, they find the angle of elevation from the street to the top of the building to be 35 degrees. They then move 200 feet closer to the building and find the angle of elevation to be 53 degrees. Assuming that the street is level, estimate the height of the building to the nearest foot. Okay, so I'm going to draw a little sketch of this. I'm going to just have that line there be the building. And I know that on a level street, so here comes my street, we've got our two students and they are looking up. Let's see, they find that the angle of elevation from the street to the top of the building is 35 degrees. So angle of elevation, nice little triangle. This is going to be 35 degrees. Okay, then what happens? They move a little bit closer. They move 200 feet. So this piece right here is 250 feet. And now they look up and the angle of elevation to the top of the building is 53 degrees, right? Now, I think we can assume that that building is been built perpendicular to the ground. So we do have a right angle in there. And our job is to estimate the height of the building to the nearest foot. So let's just let x, I'm going to say let x equal the height of the building, and that height is going to be in feet, isn't it? So I'm going to label this building as x. Okay, before I do anything else, let me just see what else I can determine here. Okay, so let me start with this smaller, I see a smaller right triangle. I actually have two right triangles, don't I? So I've got the smaller right triangle that has that 53-degree angle. And because that's in a right triangle, I know that I've got 90 degrees for the right angle. I've got 53 degrees. If I take 180 degrees and I subtract 53 degrees and I subtract the 90 degrees, what does that leave me with? That leaves me with, I think, a 37-degree angle. So this little piece up here at the top is 37 degrees. Let's see if I can squeeze that in there. What else do I know? Well, there is a larger right triangle, right? This whole big right triangle. And that one has 180 degrees minus 35 degrees minus 90 degrees. And that gets me 55 degrees. So this whole angle at the top is 55 degrees. And we know that part of that angle is 37 degrees. So that means this little sliver is 18 degrees. Now, do I know anything else? And I don't know if it's going to help me, but it's always sort of nice to just take a look and fill in anything that you can. I think I can find this angle that's down at the base that is supplementary to the 53 degrees. That 53-degree angle combined with that other angle makes up a line, a straight line, which is half of a circle. So I know that the sum of those two angles has to be 180 degrees. So if I take 180 and I subtract 53 degrees, I get, I think, 127 degrees. Does that sound right? Let me get rid of that. And I get 127 degrees right there. I don't know if that's going to help me. But let's see. Okay, so probably the easiest thing for me to do is to use my right triangle rules, right? I know that I have this 53-degree angle down at the base, and I could use SOHCAHTOA rules to say that the sine of 53 degrees is equal to the side opposite that, which would be x, over the hypotenuse. So there is the issue. I don't know, I'll call it h. I don't know the hypotenuse, but can I find the hypotenuse? I think I can. So I'm going to just hold off on what I wrote, and I'm going to say, let's just go over and look at this other triangle. I want to find h, and h is across from a 35-degree angle. I know that I have 18 that is across from 250 that was given. So that could be my anchor, couldn't it? So I'm going to say that h over the sine of 35 degrees is equal to 250 feet over the sine of 18 degrees. Now, is there another way that I could have solved this? Probably so, because I know so many angles, but this is the way that I chose to do it. I'm going to multiply both sides by the sine of 35 degrees. So I get h is equal to 250 times the sine of 35 degrees all over the sine of 18 degrees. And when I put that into my calculator, I got, let's see here, I got approximately, well, I got 464.0330846. I'm going to use all of those digits to put into the location of this h, and I'm going to solve. So I find out that x is equal to the h value times the sine of 53 degrees, except for now I know what h is. Now I'm going to go ahead and just write 464, but you all know that I'm really using all of the digits in my calculator because I don't want to have a rounding error. So when I put that 464.0330846 times the sine of 53 degrees, I got an x value that was approximately 370.59. And they do say round to the nearest foot, so I'm going to say approximately 371 feet. So estimate the height of the building to the nearest foot. I'm going to say the height of the building, is 371. And I want to make sure I put that unit of feet on there. Let's try another example. In this example, we have a pilot that's flying over a straight highway. She determines the angles of depression to two mileposts that are 4.3 kilometers apart to be 32 degrees and 56 degrees as shown in the figure below. Find the distance of the plane from point A to the nearest tenth of a kilometer. Okay, so the pilot is looking out at a horizontal, and angle of depression, remember angle of depression is if you're looking out at a horizontal and then you look down, that's 32 degrees, and that is to milepost B. And then second look down, 56 degrees, that takes us to milepost A. Okay, so that's what angle of depression is. Now, before we get ahead of ourselves, let's just identify what it is we're trying to solve for. We are trying to find the distance of the plane from point A. So distance of the plane to A. So I'm going to let that side be called x. So I'm going to actually formally write, let x equal the distance of the plane to point A. And I'm going to add the units in there because that is sort of important, isn't it? So that's in kilometers. Okay, what else do I know? Well, it was given to me that the distance between the two mileposts is 4.3 kilometers. Okay, do I know anything else? Well, I know that 32 degrees and the 56 degrees up above, within the 56 degrees, right, part of that 56 degree angle is the 32 degree angle. So I think that that means that I could find the other piece of that 56 degree angle, which would just be whatever 56 degrees minus 32 degrees is, and I think that's called 24 degrees. And that was a nice finding because notice that we now have an anchor, don't we? We know the 24 degree angle and we know the side across from it. So what that means is that if I can also determine the angle across from side X, then I can use law of sines to solve. So what is angle B? Angle B can be determined maybe by remembering some geometry. You might remember from geometry that if you have two parallel lines, and there is a line cut through them called a transversal, that alternate interior angles will be equal. So if one of those angles is 32 degrees, then the other one must also be 32 degrees. Now, if you don't remember some geometry from maybe a long time ago, consider this. Drop a perpendicular from point B to that line of sight, creating a right angle. That right angle is 90 degrees. Well, inside that triangle, this triangle, from the plane to point B to that right angle, we now have 90 degrees, we have 32 degrees, which means that this angle, the third angle in that triangle, would be whatever 180 degrees minus 90 degrees minus 32 degrees is, and that is 58 degrees. So this piece is 58 degrees. Now, because I dropped a perpendicular, I know not only that I formed a 90 degree angle with the line of sight, but I also formed a 90 degree angle with the ground. So if we know 58 of those degrees, then that inside angle is going to be complementary to the other angle, and sure enough, 58 degrees plus 32 degrees is 90 degrees. So if you remember some old geometry, that's probably the easiest way to go, thinking about the alternate interior angles. But we can also determine it just by dropping some perpendiculars. Okay, so now we know that, and I can say that x over the sine of that 32 degree angle is equal to 4.3 over the sine of 24 degrees. So x is going to equal whatever 4.3 times the sine of 32 degrees all over the sine of 24 degrees is. So when I put that into my calculator, I got approximately 5.6 kilometers. And now I'm going to write a final sentence to answer the question. The distance of the plane from point A is 5.6 kilometers, and I think I've solved it.